We're going to sketch the graph of the polar equation r equals f of theta equals to 2 times sine of theta. We'll do this in two different ways. The first way is to find an equivalent equation in rectangular coordinates. We'll multiply both sides by r. The left-hand side becomes r squared. The right-hand side is 2r times sine of theta. R squared, that's x squared plus y squared. R sine theta is y, so the right-hand side is 2y. That gives us x squared plus y squared minus 2y equals to 0. Complete the square in variable y, so x squared plus y squared minus 2y plus 1 equals 1. We added 1 to both sides, so x squared plus y minus 1 squared equals 1. And so this is a circle whose center is the point 0, 1, and radius is 1. So we sketch this graph that looks like this. This is the x-axis. In polar terminology, it's the polar axis where theta equals 0. And this is the y-axis. In polar terminology, that's the line theta equals to pi over 2. And the circle is right here. Here's the center of the circle. It's the point 0, 1. And this point up here is the point 0, 2. So r equal to 2 sine of theta is equivalent in rectangular coordinates to circle x squared plus y minus 1 squared equals 1. In this case, it was possible to take a polar equation, find an equivalent rectangular equation, and the rectangular equation was familiar, recognizable, easy to graph. Unfortunately, it is not always true that a polar equation has an equivalent rectangular equation that's easy to graph. In fact, most of the time it's false, so we need to do this directly. Let's return to our problem. R is equal to f of theta equal to 2 times sine of theta. So we're going to utilize symmetry. And there are several types of symmetries. This time we'll utilize symmetry with respect to the y-axis, which is theta, the line theta equal to pi over 2. So let's see when a polar graph is symmetric with respect to this line. So this is theta equals 0, and this is theta equal to pi over 2. Suppose we have a point right here on the polar graph. Its coordinates are r, theta. So here's angle theta, and this length here is r. If the graph is symmetric with respect to the y-axis, or the line theta equals pi over 2, then we should also have a point on the opposite side, on the other side of this line. And let's see what the polar coordinates of that point are. This is also angle theta, and the length here is r. So the angle measured from the polar axis, or from the x-axis, is this one. It is 180 minus pi, or minus theta, or pi minus theta. And so the coordinates, the polar coordinates of this point are same r, but the angle is pi minus the original angle theta. So we have just found a way to determine when the graph is symmetric with respect to the line theta equals pi over 2, or the y-axis. If the original equation is r equals f of theta, if we replace theta with pi minus theta, plug in pi minus theta into the original equation and get the same r, then we've established that the graph is symmetric with respect to line theta equals pi over 2, which is the y-axis. So now our f of theta is 2 times sine theta. And so let's evaluate f of pi minus theta. That's 2 times sine of pi minus theta. And we're going to utilize the following trig identity. Sine of a minus b is equal to sine of a cosine of b minus sine of b times cosine of a. So here a is pi and B is theta. Let's go ahead then and proceed. So we have f of pi minus theta equals to 2 times sine of pi minus theta, and that's equal to 2 times the following. So this is sine of pi cosine of theta minus sine of theta cosine of pi. Now sine of pi is 0, so this part is 0. Cosine of pi is minus 1, and so we have 2 times, this is equal to 2 times minus 1 times minus sine theta, which is sine theta, and that's the original f of theta. So we just determined that this graph is symmetric with respect to the y-axis, or the line theta equals to pi over 2. In general, this is a trig identity you should memorize, that sine of pi minus theta equals to sine of theta. And when you see sine of theta in a polar graph or in a polar equation with constants around it, and the only theta is inside the sine of theta, and this coefficient is 1, that graph will be symmetric with respect to the y-axis. So now we're going to just plot a few points and then use symmetry to take us the rest of the way. We'll just select values of theta in the first quadrant, such as 0, pi divided by 6, pi divided by 4, pi divided by 3, and pi divided by 2. Sine of 0 is 0. Sine of pi over 6 is a half, times 2, that's 1. Sine of pi over 4 is square root of 2 over 2 times 2, that's square root of 2. Sine of pi over 3 is square root of 3 over 2 times 2, that's square root of 3. And sine of pi over 2 is 1 times 2, and that's 2. So here is the graph. We'll draw big axes here so that we can have lots of room. This is the x-axis, theta equals 0, and this is the y-axis, theta equals to pi over 2. We'll draw this ray to represent angle pi over 6, and this ray will represent pi over 4, and this ray will represent pi over 3. So at 0 we're at 0. At pi over 6 we are at 1. At pi over 4 we are at square root of 2. That's a number that is larger than 1, so it'll be somewhere over here. At pi over 3 we are at square root of 3. That's bigger than square root of 2, that we're over here. At pi over 2 we're at 2, so that would be larger, somewhere over here. And now we can sketch this part of the graph. It comes out like this. Using the fact that it's symmetric with respect to the y-axis, we get an identical half of the other semicircle on this side, and we get this graph. Now this is the point 0, 2, so the center of this circle is right here in between the origin and the point 0, 2, which is the point 0, 1. Now we already knew that this is what this graph looked like, so there's no need to check any other points. But if we didn't know that, you would have to check some points in the second quadrant, because the rays in the second quadrant, the values of theta in quadrant 2, could possibly produce points in quadrant 4, because if r was negative, we would move into quadrant number 4. And then in quadrant 3, the values of theta there, if the equation was r was positive, we would have something in quadrant number 3. But in this case it doesn't happen. We already knew the graph, so we can just stop right